Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Your heavy-duty conveyor has snapped a drive shaft for the third time this quarter. The repair crew can replace it again, but what if the shaft is only the final victim? Today we will use the 5 whys to follow microscopic fatigue marks backward, from the fracture, to cyclic bending, to hidden misalignment, and finally to the maintenance control that allowed it to return. The surprise is simple: a stronger replacement shaft can still fail if the load path remains wrong. 3 failures in 12 weeks are not 3 isolated breakdowns. They are one unresolved failure loop. Every reactive repair consumes a spare shaft, rigging time, maintenance labor, and production hours. It also adds restart risk. The urgent question is not, how quickly can we replace the part? It is, why is the same fatigue mechanism still present after every repair? That is the shift from maintenance activity to reliability engineering. A single failed bearing may look like bad luck, but under magnification it can tell a story of systematic failure. A fatigue fracture typically begins at an origin, grows progressively under repeated loading, and ends in a smaller fast fracture region when the remaining metal can no longer support the load. Growth markings are clues, not automatic proof. Proper fractography is still required. Preserve the failed surface before cleaning or handling destroys the trail. Mechanical fatigue can develop under cyclic stress below the material's one-time tensile strength. In a rotating shaft carrying a transverse load, one surface alternates from tension to compression on every revolution. A crack nucleates at a local stress razor, advances cycle by cycle, and finally leaves too little intact metal to carry the load. The SN curve captures the central idea: as stress amplitude falls, expected cycles to failure rise. The plotted values here are schematic, not material data. The 5 whys is not 5 guesses, and it is not an interrogation. Each answer must be supported by evidence and must open the next level of causation. Move from the event, to the physical mechanism, to the abnormal load, to the enabling condition, and finally to the missing system control. 5 is only a guide. Branch when several causes interact, and for a high-consequence failure use 5 whys alongside metallurgical examination, FMEA, fault tree analysis, and engineering calculations. A useful investigation begins with a bounded problem statement: what failed, where, when, and under what operating condition. This is an illustrative training case, not a claim about a specific plant. We record the recurring location, the time between failures, and the field clues without yet naming a root cause. Temperature, vibration, fretting, and contaminated grease are observations. They become causes only after the team tests their relationship to the fracture. Why did the shaft break? The evidence indicates progressive fatigue. A crack began at the keyway shoulder, grew under repeated bending, and ended in rapid overload when the remaining section became too small. That statement is stronger than saying, the shaft was weak. We verify the origin, the growth region, the final fracture zone, and any similar indications on the sister shaft. A qualified metallurgical examination should confirm the mechanism before the investigation moves on. Why did the crack continue to grow? Because the corrected alternating bending stress exceeded the shaft's usable fatigue capacity. Conveyor shafts rarely see pure torque. Belt tension produces radial load, the pulley creates an overhung moment, and misalignment can add bending and bearing reaction forces. Then the keyway and shoulder concentrate the local stress. A proper fatigue screen also corrects endurance for size, surface condition, reliability, temperature, and environment. A material certificate alone cannot rescue a wrong load path. Why was the bending stress abnormally high? In this case, the investigation points to misalignment that develops under operating load. Cold alignment after a shutdown can look acceptable while belt tension, temperature, and structural deflection shift the centerline in service. That shift changes bearing reactions and bends the shaft at its most vulnerable feature. Validate the hypothesis with laser alignment, loaded pedestal movement, bearing contact patterns, and vibration trends. No single vibration peak should be treated as proof by itself. Why did the misalignment return after each repair? Because the bearing pedestal did not remain where the alignment technician left it. Lost hold-down preload, soft foot, and frame deflection can all shift the housing when the conveyor is loaded. The evidence is physical: fretting beneath shims, moved witness marks, bolt condition findings, base flatness error, and measured structural deflection. Realigning the shaft without stabilizing its foundation only resets the countdown. Why did the organization allow recurrence? The preventive task restored lubrication and replaced damaged parts, but it did not control the machine's geometry. There was no owned alignment tolerance, no loaded condition verification, no pedestal torque and base check, and no mandatory alignment trigger after bearing or coupling work. Lubrication can absolutely influence bearing life, especially under contamination. But here is the surprise: fresh grease cannot align a shaft. The root cause is a maintenance and design control gap that allowed misalignment to return. Now we screen the cyclic load. For an illustrative 80 mm solid shaft, take a fully alternating bending moment of 5 kN and mean torque of 8 kN. Apply fatigue concentration factors for the keyway and shoulder. The alternating bending stress is about 159 megapascals. The corrected mean torsional stress converts to about 193 megapascals equivalent normal stress. With a corrected endurance estimate of 220 megapascals and ultimate strength of 600, the Goodman safety factor is roughly 0.96, below 1. This is a screening example, not a design approval. A reliable design does not stop at a calculated safety factor barely above 1. If the approved target is 1.5, solving the same Goodman relation gives an allowable alternating bending stress of about 75.9 megapascals. With the same shaft diameter and fatigue concentration factor, that corresponds to only about 2.4 kN of alternating bending, less than half the 5 kN estimate. The team must reduce the bending through alignment and structural correction, redesign the stress razor or shaft, or combine these changes until the required margin is verified. Misalignment also punishes bearing life nonlinearly. Under the ISO 281 basic rating life relationship, L10 is proportional to C over P raised to a power 4 roller bearings. That exponent is 10/3. If equivalent dynamic load rises by only 20%, the relative basic life becomes 1 divided by 1.2 to the 10/3 power, about 0.545. In other words, roughly 45% of basic rating life disappears. ISO 281 defines basic rating life at 90% reliability, and its modified approach considers lubrication and contamination. Before closing the root cause analysis, prove every link. Preserve and examine the fracture. Measure alignment, runout, soft foot and loaded pedestal movement. Reconstruct belt tension, torque, current and startup transients. Then correlate vibration, temperature and lubricant condition with operating load. Most physical inspections require hazardous energy isolation. If energized testing is necessary, it must follow a controlled, authorized procedure with appropriate safeguards. The goal is not a persuasive story, it is a causal chain that survives measurement. The solution works in layers. First, contain the risk, isolate the equipment, and preserve the evidence. Next, correct the physical condition, stabilize the base, align the train under a defined condition, and verify belt load. Then check whether the shaft, keyway, fillet, bearing, and coupling meet the required fatigue margin. Build prevention into the maintenance system through load-appropriate lubrication, alignment triggers, and hold-down audits. Finally, verify stable loaded vibration, acceptable stress margin, and absence of recurring cracks. Running again is not the same as solved. The 5 answers now form one verified chain. The shaft failed by fatigue. Fatigue was driven by excessive cyclic bending. The bending came from misalignment under load. Misalignment returned because the pedestal and support were not stable, and the maintenance system never owned or verified precision after intervention. That is how 5 Whys transforms a broken component into a reliability system. What component in your plant has failed more than once? Share it in the comments, and subscribe to SimpleGAN for practical industrial engineering.
Imagine a pressure vessel designed in the United States, manufactured in South Korea, fitted with a German motor, installed in India, and operated by a multinational company. Its design follows ASME, its steel ASTM, and its electrical equipment IEC. Which of these, BIS, ISO, IEC, ASME, or ASTM, is the highest standard? The surprising answer is none of them. There is no global ranking. They operate at different levels and solve different engineering problems. Standards create a common technical language. They define requirements for dimensions, materials, safety, testing, and quality systems. Without them, a bolt from one country might not fit a nut from another. Remember, a standard is not automatically a law. Most are voluntary when published. They become mandatory only when referenced by national legislation, technical regulations, or specific contracts. BIS is India's national standards body, established in 1987. Standards published by BIS carry the prefix IS. They also operate product certification and hallmarking schemes, including the familiar ISI mark. BIS also adopts international standards, designated as IS/ISO or IS/IEC. It represents the national standards layer for India, just as BSI serves the UK or DIN serves Germany. ISO stands for the International Organization for Standardization. Established in 1947, its scope is broad, covering everything from ISO 9001 for quality management to ISO 27001 for information security. A common misconception is that ISO itself certifies companies. It does not. ISO develops the standards. Independent certification bodies perform the audits to evaluate quality and process control. IEC specializes in electrical and electronic technologies. Its standards deal with motors, transformers, and industrial automation. While ISO is broad, IEC focuses primarily on electricity and electronics. ASME, originally the American Society of Mechanical Engineers, is influential in mechanical design. Its BPVC code is used in over 100 countries, providing detailed rules for designing and manufacturing equipment. ASTM International specializes in materials and testing methods. While ASME tells you how to design a vessel, ASTM specifies the properties and testing of the steel used to construct it. However, ASTM and ASME designations are not always interchangeable. Engineers must check the applicable ASME code edition and project specifications before substituting materials. Global engineering relies on all five working together. An industrial reactor may be designed to ASME, use ASTM steel, have an IEC motor, and require BIS compliance for the Indian market. Beware of 4 dangerous misunderstandings. International standards don't override national law. The newest edition isn't always the contractually required one, and never mix systems without checking compatibility. Before selecting a standard, ask, where will it be installed? Which laws apply? Which design code is specified? The most important organization depends entirely on the engineering problem at hand. Standards are interconnected layers of engineering knowledge built from a century of research and lessons learned. Together, they allow global engineering to work. This is Simple Gyan.